Good morning, children. Today we will be studying about standard hydrogen electrode or normal hydrogen electrode. Before we start up with the class, just a reminder, we have already studied about the electrochemical cell in which the chemical energy is converted into electrical energy and due to separation of the charges between the electrode and solution, electric potential is set up between the metal electrode and its solution. This is called electrode potential. Basically, there are two types of electrode potential which can develop. One is oxidation potential, which is the tendency to lose electron, and second is the reduction potential, that is the tendency to gain electrons. Electrode potential depends upon nature of metals and its ions, concentration of ions in solution, and temperature. So now we will start about standard hydrogen electrode or normal hydrogen electrode. It consists of a platinum wire. This wire you can see is a platinum wire which is kept in a sealed glass tube, and we have a platinum foil attached to the platinum wire. The foil is coated with finely divided platinum which acts as platinum electrode. Now hydrogen gas at 1 atmosphere is pumped into this vessel, and we have 1 molar HCl in the beaker. Pure hydrogen gas at 1 atmosphere is constantly bubbled into the solution at 298 Kelvin. The surface of this foil acts as both cathode as well as anode. So that means standard hydrogen electrode is a reversible electrode. That means it can act as both cathode as well as anode. So when SHE acts as anode, the reaction taking place is that hydrogen gas loses 2 electrons and gets converted to hydrogen ion. So, and when SHE acts as cathode, then hydrogen ion accepts 1 electron and gets converted to hydrogen atom. Two hydrogen atoms combine together to give hydrogen gas. Electrode potential of standard hydrogen electrode is taken always as 0. It is used to calculate electrode potential of various metals. If suppose in exam we find a question that find out the electrode potential of zinc. Now how this is to be calculated? If standard hydrogen electrode acts here as anode, then we are already aware of the equation that E naught cell is equals to E cathode minus E anode. So substituting the value, where you are aware about the electrochemical series also, from there we can find the value of E naught cell of zinc. So E naught cell value for zinc is negative 0.76. This is equals to electrode cathode E cathode minus 0, which is standard hydrogen electrode. So E cathode will be equals to minus 0.76. So we can always find out the value of E naught for zinc, that is minus 0.76. Another question we can take is calculate E naught cell when copper 2 plus copper is equals to 0.34 volts, and for zinc with this electrode potential has been given as minus 0.76 volts. So E naught cell will be E cathode minus E anode. E cathode here is 0.34 minus 0.76. Always the higher value will be the value for the cathode, and then we can find out the answer for E naught cell. Now we will be studying about Nernst equation. For the reaction, suppose we consider one reaction, Mn positive in aqueous medium plus n number of electrons gives M metal which is in solid state. So by Nernst equation, the expression can be written as E cell is equals to E naught cell minus 2.303 RT by NF log of the product upon reactant. That is M solid divided by Mn plus aqueous. Now if the reaction takes place at 25 degrees Celsius, that means 298 Kelvin, then we can substitute the values, and our E naught cell will be equals to E cell will be equals to E naught cell minus 2.303. Now R here is a gas constant, T is temperature, N is the number of electrons which are being exchanged, and F charge in Faraday. So substituting the values 2.303 into our value of gas constant is 8.314 into temperature we have taken is 25 degrees Celsius, that means 298 Kelvin, divided by n, where n is the number of electrons which are being exchanged, multiplied by 1 Faraday, that is 96500 Coulomb. Log of, now for solid substances we take the value of concentration as 1, so 1 upon mn plus aqueous. This value, once we calculate it, the value comes out to be equals to 0.059. So our E cell value becomes equal to E naught cell minus 0.059 by n log 1 upon mn plus in aqueous. And so we can have a generalized expression, and that is E cell is equals to E naught cell minus 0.059 by n log of cathode by anode. This is the generalized equation for, or we can say this is the generalized Nernst equation. We learn to calculate now the equilibrium constant for Nernst equation. So the EMF of the cell may be used to calculate the equilibrium constant for the cell reaction. At equilibrium, both the electrode potentials of the two electrodes becomes equal, so that EMF of the cell will be equals to 0. Now we take an example of the redox reaction, zinc plus copper ion. It's a reversible reaction because it's a redox reaction. So zinc ions plus copper. Now at equilibrium, as the reaction progresses, there will be a decrease in the concentration of copper ions. As a result, the reduction potential of copper cathode decreases and the reduction potential of anode, that means zinc, increases. At equilibrium, both reduction potential will be equal, right? So assuming that the concentration of zinc is Zn plus 2 plus aqueous and copper is copper 2 plus aqueous. So at equilibrium we have the equation K. Equilibrium constant will be equals to zinc 2 plus copper solid divided by zinc solid and copper 2 plus. Because zinc in solid state and both copper, the value of both of them will be equals to 1. So we have the final equation as K is equals to zinc 2 plus ions aqueous divided by copper 2 plus aqueous. Therefore, the value of E cell will be equals to 0 at equilibrium, because the rate of forward reaction is equals to the rate of backward reaction. So we can say from the equation of the E cell that it will be 0 is equals to E naught cell minus 2.303 RT by 2F. Now why 2F? Because we have a net exchange of 2 electrons. That is why we have replaced the value of n by a factor of 2. So we get the expression 0 is equals to E naught cell minus 2.303 RT by 2F log of zinc ions upon copper ions. Now since this value is equals to K, because this is the equilibrium constant, so we can substitute the values and we get the expression E naught cell is equals to 2.303 RT by twice of F log of K. We can understand here the relationship between the electrochemical cell and the Gibbs energy. We are aware that electrochemical cell is a cell in which chemical energy is converted into electrical energy, and the chemical energy involved is a spontaneous reaction, and for all spontaneous reaction, change in Gibbs free energy is always negative. In an electrochemical cell, the chemical energy is converted into electrical energy. The cell potential is related to the Gibbs free energy change, and we are aware that delta naught G is equals to maximum work done. That means electrical work done in 1 second is equal to electric potential multiplied by total charge passed through the solution multiplied by the number of electrons for a spontaneous reaction. And from this we get the expression delta G naught is equals to minus NF E naught cell. Why we are getting a negative sign over here? Because for spontaneous reaction, change in free energy will be negative. Now from standard Gibbs energy change, we can calculate the equilibrium constant by the reaction delta G naught is equals to minus RT log of K. This equation helps us to predict the feasibility of a reaction, of any spontaneous reaction of that matter. Delta G should always be negative, for which it is important that E naught cell, this E naught cell should be having a positive value. If this has a positive value, then only we will get the standard free energy changed as negative for the spontaneous reaction. So for the electrochemical cell and Gibbs energy, we should remember this relationship: delta G naught is equals to minus RT log of K.